Hello children, good morning to all of you. Welcome back to physics class. Today we are going to start your last chapter, magnetism. I hope you have remembered what is a magnet. Children, in your earlier classes you have studied that magnet is a substance which attracts some magnetic materials. You also have studied that the first natural magnet was lodestone, which was an iron ore, iron oxide. This lodestone had some property. It attracts some iron pieces, and when it is suspended freely, it always comes to rest in north and south direction. But for different purposes, artificial magnets have been prepared. The reason is the natural magnets are not magnetically very strong. That is why artificial magnets in different shape and size have been made, just like bar magnet, horseshoe magnet, compass needle, etc. Children, we know that when a magnet is suspended freely, it comes to rest in the north and south direction. So, the end of the magnet which comes to rest in the north direction, that is called north pole, and the end of the magnet which comes to rest in the south direction, that is called the south pole. Now, when we bring two magnets together, so if north and north pole are bringing together, they will repel each other. If north and south poles are brought together, then they attract each other. So we can see that opposite poles attract each other and similar poles repel each other. These are some common properties of magnets which you have studied also. Now in this class, you are going to study about the induced magnetism. But before that, note down these things. Okay, now we are going to see induced magnetism. Children, induced magnetism is a temporary magnetism. Actually, when one magnetic material is brought near a magnet, try to understand. Suppose this is a magnet and this is one magnetic material like iron or steel or nickel or cobalt, anything. Okay, so when a magnet is brought near are in contact with a non-magnetic material, then the non-magnetic material also behaves like a magnet. Try to understand. When an unmagnetized material is brought near a magnet or in contact with a magnet, then this unmagnetized material also behaves like a magnet. Means in this situation, if we bring the iron nails near it, then it will cling to it. It means because of this magnet, this unmagnetized material also behaves like a magnet. So this is called induced magnetism. This unmagnetized material is gaining the property of magnet in the presence of another magnet near to it or within contact. Understood? This type of magnetism is called induced magnetism. You have to remember, induced magnetism is a temporary magnetism. A material will behave like a magnet only till it is kept near a magnet. When a magnet is removed, then it will become again a normal material. Now it will not behave like a magnet. Understood? So the temporary magnetism acquired by a magnetic material when it is kept near or in contact with a magnet is called induced magnetism. And this process is called magnetic induction. So what is the magnetic induction? The process in which a magnetic substance acquires the magnetic properties temporarily in presence of a magnet, it is called the magnetic induction. Now children, you will see that if a magnet is kept near an iron bar, then this iron bar will also behave like a magnet. If we check the polarity of this iron bar, we will see that this will be the south pole and this will be the north pole. When iron bar is brought near the magnet or in contact with magnet, then this iron bar will also behave like a magnet. And if we check the polarity of it, since it is a magnet now, so again it has two poles. So we will find that near the north pole of the magnet, the south polarity will be created in the magnetic substance, and at the other end north polarity will be created. So this property you have to learn. Now we will see magnetic field lines. Okay. Now see the magnetic field lines. Actually children, around a magnet there is a definite region in which magnetic force can be felt. You have to remember this point. Magnet can attract an iron nail piece at a certain distance. If we keep the iron nail more than that distance, then it will not be attracted by the magnet. It means magnet can apply a magnetic force in a certain region around it. That region is called magnetic field. Okay, and children, we see that if near a magnet, if we bring the compass needle, then the needle will be directed towards the pole. But if we displace the needle in different direction than the pole, then the needle direction will also be different. It means the direction of magnetic force is always different at different places. So if we draw a curve of the magnetic force, then this type of curve we are getting, and these lines are called the magnetic field lines, which shows the direction of the magnetic force applied by the magnet. Understood? Magnetic field lines are vector quantity. You have to remember this point. Okay, say here, the region around a magnet in which magnetism is felt is called the magnetic field of the magnet. It is a vector quantity. And how will you define the magnetic field lines? Say here, a magnetic field line is a continuous curve in a magnetic field such that tangent at any point of it gives the direction of the magnetic field at that point. This experiment can be done by taking a magnet. Take one bar magnet, keep on a plain paper, and then iron fillings are spread around the magnet. Then after some time we will see that the iron fillings will be arranged in this way. The diagram which I have made here, the iron fillings around the magnet will be spread in this direction. We will notice that no field lines will intersect each other. It means at every point the direction of the magnetic force is different, and the magnetic field lines moves from north to south direction. Okay, the direction of the magnetic field lines is north to south direction. Okay, now we will see the properties of magnetic field lines. Okay, now see the properties of magnetic field lines. As we have seen that magnetic field lines are the vector quantity and its direction is from north to south pole. So see one by one. The first, they are closed and continuous curves. Children, when I draw the graph here, previously you have seen at the pole the lines are very near to each other, but in the middle of the magnet the magnetic field lines are away from each other, but we are watching the continuous curve from north to south pole. Second one, outside the magnet, the magnetic field lines are directed from north pole towards the south pole. Okay, inside the magnet, the direction of magnetic field is south to north, but out of the magnet, the direction of field is north to south. Third point is, the tangent at any point on a field line gives the direction of magnetic field at that point. Okay. The fourth point is, the magnetic field lines never intersect each other. Very important point, you have to learn it. The magnetic field lines will never intersect each other. And magnetic field lines are crowded at the pole and far separated near the middle of the magnet. The reason is at the pole, the magnetism is maximum. The magnetic force of a magnet is maximum at the pole, and it is reduced when we move from pole to middle. That means magnetic force is minimum at the midpoint of the magnet and maximum at the pole. That is why magnetic field lines are crowded at the end and far separated in the middle of the magnet. Okay, and parallel and equidistant field lines represent a uniform magnetic field. Magnetic field lines are parallel to each other, that is why they never intersect each other. And children, our earth also behaves like a magnet, but about this we will discuss in the next one. For today only this much. Read carefully your chapter, and whatever you want to ask, you can ask me by messaging in the classroom. Okay, bye bye.